opportunity in the first two sessions to hear a lot about how we can leverage AI to help important vulnerable populations and how to think about fairness and robustness when using algorithmic models in social setting. However, we also can have a great social impact in the area of environmental sustainability as well. So Sustainable Development goals cover a broad set of topics, including human well-being as well as other species well-being across the world. So in this session, we're going to hear more about things related to those topics. And so I wanted to briefly share with you some of the work that we've been doing on using AI for habitat and species conservation. As you know, all know, protecting biodiversity is one of the key sustainability goals. And the situation with habitat loss and species loss has progressively becoming more and more dire, with 10 to 30% of mammal, bird, and amphibian species currently being threatened or extinct. And with climate change and its accelerating pace, that becomes even more pressing issue. And so AI can really play an empowering role in addressing some of these challenges in many different ways. At USC, we have used AI to help leverage satellite data in order to inform conservation, and I'll share some of that with you today. We also can use statistical AI models to learn how species use habitats and how these habitats will change under climate change in order to predict how species richness will change and how we might need to change our conservation strategies. Another aspect that we work on a lot is developing new decision tools, spatial planning tools that can inform planning in terms of conservation actions. Where should we protect the next conservation site? Where should we build wildlife corridors to enable species migrating or moving to new habitats under pressures both from climate change and humans? And as well as how we can leverage AI to address the second biggest threat to wildlife, which is actually illegal poaching and trafficking. And so today I'll just quickly touch on the first two, but you'll hear a little bit about our anti-trafficking sessions from Aaron in a minute. So what is land cover mapping and why is it important? Land cover mapping is basically understanding each pixel on Earth, what kind of land cover it has. Is it forest, water, field, built environment, etc. Having this information at high resolution is extremely important. It can inform conservation efforts by understanding where we have certain types of habitat. It can detect illegal logging or illegal mining in protected areas. It can show urban growth. And so satellite data is one of the most ubiquitous and empowering data sources that we have today. And the beautiful thing about it is that we have it available across the world, both in developed and underdeveloped areas. But how can we leverage more effectively? So as I said, it can help us for conservation, for example, by identifying important areas for riparian conservation. So these are like possible forested areas next to rivers. And so our partners in this endeavor, which is the Chesapeake Nature Conservation Conservancy, was really curious about how they can scale up the efforts that they had already put into using satellite data. However, they had paid 1.3 million to have basically manual or semi-manual labeling of the satellite data in the Chesapeake Bay in order to do this kind of riparian analysis. And so in our project, we are basically trying to say, well, how can we actually help scale this up and be able to do this kind of analysis across the US? So 98% of the US, we don't really have that kind of high resolution label data, but we obviously would like to. And so here is kind of the setup. We have a lot of satellite data, very high resolution satellite data, but in terms of the labels, we only have the Chesapeake Bay area where the Conservancy put their money to label. We also have coarse labels, like a 30-meter resolution label at national level. So how can we combine those two sources of label data in order to be able to predict or extrapolate this high resolution, 1-meter resolution land cover mapping labels, which are the resolution at which we need the actual data to make informed decisions. So we developed a special deep learning approach, which basically leverage both very coarse resolution and very limited high resolution data, which is based on the idea of this super resolution blockwise comparison, where we basically, wherever we have high resolution data labels, we use it. And in places where we don't have the high level resolution labels, we still predict at this high resolution, but then we summarize on the coarse resolution where we can have signal from the existing coarse labels. So based on this new deep learning architecture, we were able to train a model and apply it over the 8 trillion pixels of satellite data across the whole continental US. In our close collaboration with Microsoft Research, which also allowed the computational resources that something like that required. So at the end result of this was creating the very first US-wide high-resolution 1-meter land cover map, which now is being used by a lot of different initiatives and conservation actions and NGOs. One important thing, though, is that for this to actually apply to new areas, right? So new habitats where are very far away from the kind of data that we've seen before, we need to be able to find this to tune these models quickly. And so in order to do that, we want to be able to leverage humans, domain experts that are local to that area, to take this big model trained across a large area, but specialize it to the area of interest. So there's a domain shift, so there might be some changes in the way that different kind of land covers look like. So we built this interactive tool that allowed for human-in-the-loop labeling. And so here you see some images of that, where you can overlay the satellite images together with the predictions of the models and explore those across the area that you know as a user. And so then you can interactively flip between the predictions and the actual images and decide where it's making mistakes and manually enter strategically corrections into the data set. This is immediately sent back to the server, and the model is fine-tuned with these additional labels. And then you can keep on doing and panning, and the user can basically decide which are the most critical errors that it needs to give additional information to the model in order to update as fast as possible. And then you can keep on applying this. So at the end result, you can basically extrapolate this fine-tuned model to the area that you care about. So the important thing that we leveraged in this is often when people think about human-in-the-loop in machine learning pipelines, they're using the humans only as labelers. Basically, the algorithm decides which data we are still missing and then gives it to a human who just labels it. The important difference here is that the domain expert is seeing the maps and they're deciding actually which pixels need to be corrected. They're not just being pointed by an algorithm, is like correct here, because basically the human ability to see the visual context and understand a bigger picture of some kind of pattern in the kind of errors that the model is making, the user is able to much better decide which things will be the most informative one. And so we basically created an actual controlled experiment using Amazon Mechanical Turk, where we had people do these interventions, this data labeling under different conditions in different areas of satellite data, and showed that indeed expert domain users are able to much quicker fine-tune those models to improve the performance to a completely new area than just simply algorithmic decision-making of which things have to be relabeled. And so currently this model is actually being used by Microsoft AI for Good with multiple partners and extrapolating to things in places in Asia and in Africa, and working with local NGOs in specific locales to basically help them understand the land cover situations and plug this into different kind of actions. So time is up. So I wanted to quickly share some of on the other three topics. Understanding species changing habitats under climate change is another extremely pressing issue. And so we have also developed a framework, a package that is able to take environmental data, current species occurrences, climate change projections, and develop these species distribution models that are able to inform us on predicted future biodiversity, but more importantly, is also able to generate maps under both climate change as well as species dispersal limits. So the biggest problem in already the projections are pretty dire, but when you incorporate the fact that animals cannot follow the shifting habitats because of the climate change, then the situation is even more dire than expected. And so, so some of these results are also extremely important and can help, again, conservation action. So I'm going to stop here and just say that we're going to hear about our work on illegal wildlife trade and how we can use AI in a follow-up talk in this session. Thank you.